An explosive material, also called an explosive, is a reactive substance that contains a great amount of potential energy that can produce an explosion if released suddenly, usually accompanied by the production of light, heat, sound, and pressure. An explosive charge is a measured quantity of explosive material. This potential energy stored in an explosive material may be chemical energy, such as nitroglycerin or grain dust; pressurized gas, such as a gas cylinder or aerosol con; nuclear energy, such as in the fissile isotopes uranium-235 and plutonium-239. Explosive materials may be categorized by the speed at which they expand. Materials that detonate are said to be high explosives, and materials that deflagrate are said to be low explosives. Explosives may also be categorized by their sensitivity. Sensitive materials that can be initiated by a relatively small amount of heat or pressure are primary explosives, and materials that are relatively insensitive are secondary or tertiary explosives. A wide variety of chemicals can explode. A smaller number are manufactured specifically for the purpose of being used as explosives. The remainder are too dangerous, sensitive, toxic, expensive, unstable, or decompose too quickly for common usage. In contrast, some materials are merely combustible or flammable if they burn without exploding. History. Though early thermal weapons, such as Greek fire, have existed since ancient times, the first widely used explosive in warfare and mining was black powder, invented in 9th century China. This material was sensitive to water, and it produced dark smoke. The first useful explosive stronger than black powder was nitroglycerin, developed in 1847. Since nitroglycerin is a liquid and highly unstable, it was replaced by nitrocellulose, smokeless powder, dynamite and gelignite. World War I saw the introduction of TNT, trinitrotoluene, in artillery shells. World War II saw an extensive use of new explosives. In turn, these have largely been replaced by more powerful explosives such as C4 and PETN. However, C4 and PETN react with metal and catch fire easily, yet unlike TNT, C4 and PETN are waterproof and malleable. The increased availability of chemicals has allowed the construction of improvised explosive devices. Applications. Commercial. The largest commercial application of explosives is mining. Whether the mine is on the surface, or buried deep underground, there are often times when the use of either a high or low explosive in a confined space can be used to liberate a fairly specific subvolume of a brittle material in a much larger volume of the same or similar material. Normally the material we are talking about in mining is a ceramic of some kind. If there are mineral deposits where large masses of native metal are present in the ground, using explosives to liberate the ore typically doesn't work well. In materials science and engineering, explosives are occasionally used in cladding. A thin layer of some material is placed on top of a thick layer of a different material, both layers typically being metal. On top of the thin layer is placed an explosive. At one end of the layer of explosive, the explosion is initiated. The two metallic layers are forced together at high speed and with great force. The explosion spreads from the initiation site throughout all the explosive. Ideally, this produces a metallurgical bond between the two metallic layers. As the length of time the shock wave spends at any point is small, we can see mixing of the two metals and their surface chemistries through some fraction of the depth, and they tend to be mixed in some way. It is possible that some fraction of the surface material from either layer eventually gets ejected when the end of material is reached. Hence, the mass of the now welded bilayer may be less than the sum of the masses of the two initial layers. There are applications where a shock wave and electrostatics can result in high-velocity projectiles. Military civilian safety types. Chemical an explosion is a type of spontaneous chemical reaction that, once initiated, is driven by both a large exothermic change and a large positive entropy change in going from reactants to products, thereby constituting a thermodynamically favorable process in addition to one that propagates very rapidly. Thus, explosives are substances that contain a large amount of energy stored in chemical bonds. The energetic stability of the gaseous products and hence their generation comes from the formation of strongly bonded species like carbon monoxide, carbon dioxide, and nitrogen, which contain strong double and triple bonds having bond strengths of nearly 1 megajoule mole. Consequently, most commercial explosives are organic compounds containing NO2, ONO2 and NHNO2 groups that, when detonated, release gases like the aforementioned. An explosive is classified as a low or high explosive according to its rate of burn. Low explosives burn rapidly, while high explosives detonate. While these definitions are distinct, the problem of precisely measuring rapid decomposition makes practical classification of explosives difficult. Decomposition. The chemical decomposition of an explosive may take years, days, hours, or a fraction of a second. The slower processes of decomposition take place in storage and are of interest only from a stability standpoint. Of more interest are the two rapid forms of decomposition, deflagration and detonation. Deflagration. In deflagration, decomposition of the explosive material is propagated by a flame front which moves slowly through the explosive material, in contrast to detonation. Deflagration is a characteristic of low explosive material. Detonation. This term is used to describe an explosive phenomenon whereby the decomposition is propagated by an explosive shock wave traversing the explosive material. The shock front is capable of passing through the high explosive material at great speeds, typically thousands of meters per second. It is any device or material in which the explosive is ignited, thereby reaching a reactive incident. Exotic. In addition to chemical explosives, there are a number of more exotic explosive materials, and exotic methods of causing explosions. Examples include nuclear explosives, and abruptly heating a substance to a plasma state with a high-intensity laser or electric arc. Laser and arc heating are used in laser detonators, exploding bridge wire detonators, and exploding foil initiators, where a shock wave and then detonation in conventional chemical explosive material is created by laser or electric arc heating. Laser and electric energy are not currently used in practice to generate most of the required energy, but only to initiate reactions.